A bit is a word that we use to represent a digit in binary system. A bit is going to be a 0 or a 1, or on or off. So we have these little boxes in your computer's memory, each one able to store an on or off state. All right, so a bit is one of these boxes that's going to be either on or off. 8 of these boxes, when they come together, we call it a byte. These 8 will make up 1 byte. And this sort of separation is going to be constant. We're not going to move the byte boundaries around. So in your memory, in your computer's memory, the first 8 will be the first byte. The second 8 will be the second byte. In most programming languages, a byte and a character are the same thing. In MATLAB, 1 character is actually represented by 2 bytes. Let's look at decimal to binary conversion. When you have a decimal number and you want to convert it to binary, you're going to think about these little bits. The number of bits we have is going to depend on the data type that we are trying to store the number into. But for the sake of conversion, we're just going to create as many boxes as we need. The one on the very right will have a value of 1, so that's my pennies. Next one over is going to have a value of 2 cents, 4 cents, 8 cents, 16 cents, 32 cents. Okay? So these are my coin types. So rather than having 1, 5, 10, I have 1, 2, 4, 8. And then I will take the number 17. I will repeatedly, starting from the highest one and then going down, I will ask, do I have that many cents? If so, how many of them do I have? Do I have a 32 cent within 17 cents? No. So this is the amount I need to pay to the customer. I'm trying to break it down to coins. One coin type is worth 32 cents. And then I have to decide, do I give the customer this coin? And the answer is no. The next one over is a slightly smaller coin, half the size, and it's worth 16 cents. Do I give the customer one of these coins? Yes, I do, because I have to give them a total of 17 cents. I'll give them a 16-cent coin, and then I will keep track of how much more do I owe them. How much more do I have to pay them? 17 minus 16. I owe them 1 more cent. 1 cent left. And then I will ask, do I have to pay them an 8-cent coin? No. Do I have to pay them a 4-cent coin? No. A 2-cent coin? No. Do I have to pay them a penny? Yes. So I paid them a penny. I'll subtract. I end up with 0. And this is my binary number. So my binary number is 0, 1, 0, 0, 0, 1. The 0 at the very beginning is optional. Even if I remove it, this is still the binary number. The pennies should always be listed on the very right. So the number on the very right, the digit on the very right, is your least significant digit. If you find your binary number and you want to double check your answer, you can do that easily. So let me rewrite the number that we found. 1, 0, 0, 0, 1. And write down the value of each coin type. 1 cent, 2, 4, 8, 16. You're just going to multiply each coin type that you gave to the customer and how many of them you gave to the customer. We gave them 1 penny, which totals to 1 cent. And we gave them a coin whose value is 16. So that means we gave them a value of 16 cents for that coin. When we add it up, that means we gave them a total of 17 cents. So that's how you can take a binary number and find out the decimal value of it. Okay? So when you start from decimal, you repeatedly ask, can I give this coin type? And how many of them do I give? And keep doing that until you don't owe the customer anything anymore. When you go the other way, you multiply the value of each coin type with how many of those coins you gave to the customer, and you get the answers by adding them up. In binary system, these will always be either a 1 or a 0. But in other systems, the number could be other than 0 or 1. Okay? Such as with coins, The number on the very right could be 0, could be 1, could be 2, 3, 4, can be 5. So with our regular coins, the pennies digit cannot be 5. Because if it were 5, we could just take those 5 cents and give them a nickel instead. Hexadecimal is a fancy word that we use to state that it is a base 16 number. And it is conventionally shown with the notation 0x. If you are given a number that has 0x at the beginning, you will have to know that it's a hexadecimal number. So let's look at the hexadecimal numbers. The same sort of steps, but the value of the coins are different. So just imagine you are in a different country that uses a different set of coins. They will always have pennies. So the one on the very right is worth 1 cent. Next one over, they have a 16-cent coin. Next one over, they have a coin that is worth 256. So it's powers of 16s. Base 16 means every digit has a value 16 times the previous digit. All right, so these are the coin types I have. We have a 1, and everything else is zeros. So you don't have to really write those boxes. I have given them a penny, which has a value of 1. I have also given them a coin that has a value of 16 cents, which means I gave them, in total, I gave them 17 cents. So 0x11 in hexadecimal is worth 17 in decimals. I can go the other way, 17, and break it down to coins, 1, 16, 256. The process that I will follow will be similar to what I did with breaking money into coins. So I will ask, do I have to give them a giant coin that is worth 256 cents? No, so that will be a 0. And then I will look at my next coin type, which is 16. Do I give them this coin type? Yes. How many of them do I give? Just 1. So I will give them 1 16 coin type. And I have given them 16 cents. I have 1 cent left to go. And I'll just give them a penny and be done. Let's do 241 as an example. And I have to give the customer a total of 241 cents. Do I give them 256 coin type? No. Do I give them 16-cent coins? Yes. And now I have to ask, how many of such coins do I have to give them? I have to give them 15. So it's 241 divided by 16 is 15. So that means I have to give them 15. And now I'll have to check how much did I just give them. I just gave them 240 cents total. I'll subtract from the total amount that I owe them. I need to give them 1 more cent, and I can just give them a penny. So I gave them a penny, and I gave them 240 cents. I gave them a total of 241 cents. When I draw the boxes, the separation is clear. But if I want to write this down as an email and say I gave somebody in hexadecimals 151, the separation is lost, right? I don't know if it is 1 and a 5 and a 1 or 15 and 1. So I have to make sure that when I write this out, I maintain the separation. The convention when you write hexadecimal numbers is to introduce additional digits, additional letters that will represent digits higher than 9. So if you have a 10, instead of writing 10, you're going to write A, the letter A. If you have 11 in a box, you will replace that with the letter B. 12 is replaced with the letter C, 13 with the letter D, 14 with the letter E, 15 with the letter F, 16 with the letter G. Nope, we don't have number 16 in hexadecimal. So we do not have G. The largest number we can have in each box is 15. We had 15 and 1. When we write this out as text, we're going to write out F1 and put 0x in front of it to indicate that this is a hexadecimal number. When you create a number, when you store a number in a variable in MATLAB, it automatically becomes a double data type. When you look at the workspace, it will show you a class is double. A double is a floating point number, so it is able to store numbers that have point something. Single is also used to store floating point numbers, but it is not as precise. It has fewer bits dedicated to it. More precisely, double has 64 bits, 8 bytes. So remember, each byte is 8 bits. A double takes up 8 bytes room from your memory. So 64 little boxes are used to store a number. So when you say A equals 5.6, that number 5.6 has to be converted into zeros and ones. And after this has been converted, some of these bits are going to be on, and some of them are going to be off. And this pattern of ones and zeros will represent your number 5.6. If you have 64 bits compared to 32 bits, you can store more numbers, right? You have more options. Single is 32 bits. You have less precision. You cannot store as large of numbers as you can with the double, or as small of numbers as double. Real max is a function that will tell you the largest number you can represent in MATLAB using the double data type. Real max, it's a function. 10 to the power 308 is the largest number we can store in a double data type. So if you say A equals to 10 to the power 307, you are able to store it. But if you say 309, you cannot store it. MATLAB will replace that with infinite. Similarly, real min will tell you the smallest number you can represent in MATLAB, 10 to the negative 308. That's 0.00308 zeros followed by a 2. If you try to store a number smaller than this, it may become 0, or it may be replaced with smallest number. 10 to the power negative 340 is replaced with 0. So it's smaller than the smallest number we can represent. So MATLAB just replaces that as 0. So it's important to keep this in mind. You cannot represent infinitely many numbers. There's a limit on the absolute value and also on the precision of the numbers you can store.